Hi there, it's Mr. Ray again with our next lesson in grade 12 vectors. We are working in the Introduction to Vectors unit, and we're going to continue on with our algebraic operations with vectors. Our previous lesson we looked at algebraic operations with vectors in 2-space, or R2. So today we're just extending that into 3 dimensions, R3. Now, it's very, very similar, except we're adding a third dimension. So in terms of our coordinate system, with R3 we now have the Z coordinate as well as the X and Y, which we already had in R2. And in terms of our basis and component vectors, well, the standard basis vectors, we still have the I hat and j hat vectors, which are unit vectors along the x and y axis respectively. And we've now added this k hat vector, which is a unit vector along the z axis. So we need that in order to identify any vector in R3. So our component vectors in R3 are the I hat, j hat, and k hat. You can see it written as components. One unit I hat is 1 unit in the along the x-axis, j hat is 1 unit in the y-axis, and k hat is 1 unit along the z-axis. So we've just updated those unit vectors to have 3 dimensions and also to add the k hat. So this is a position vector, could be represented as components. We put it in square brackets to show that it's a vector, not a coordinate. So those would be the scalars multiplying with I hat, j hat, and k hat, or you could write it out as a sum of the three standard basis vectors with that a, b, c scalar multiples. If you want to get the magnitude of a vector, in this case the position vector OP, this is kind of an updated version of Pythagorean theorem, except now under the square root we've added the third component, which would be the c squared, which, and remember c is the scalar multiple of the k hat, or the third component for the vector. So we'll look at a couple examples using that. In terms of getting two points in space A and B in 3 space, to get the components or the resultant vector of AB, it's still the same formula as we had in 2 space. It's OB minus OA. So basically the 2 position vectors subtracted in that order. And algebraically, we're just subtracting the components of OA from OB. Okay, and this is kind of a expanded version of the definition of OP. So if we want to get the magnitude of any vector AB, it's the difference in all the components squared, added together, and then square rooted. Okay, now in terms of the representation of these vectors in R3, R3 is definitely more complicated to imagine because of the fact it's 3-dimensional, and trying to show that on a 2-dimensional piece of paper is a little difficult. So we've only drawn our positive. Here's our positive x-axis, our positive y-axis, our positive z-axis. If I want to show a point or a vector in 3 space, I first look at the x component. So the value of the x, if I'm looking at a point, I'm looking at the x coordinate. So I move along the x-axis that many units. I stop, so that would be the point, whatever a is, a0, 0, and then I look at the second value, the y coordinate, which in this case is b. So I move b units. I move in a line that's parallel to the y-axis from where I left off, and that length of that line would be b units. I stop right here. So basically it's a three-step procedure. The first step is along the x-axis to the point on the x-axis, then move parallel to the y-axis from that point we just made, that in this case B units along, stop there, and then we move C units up or down from that second point we just made, and at that third point, that is where we would draw that point ABC. And then in terms of drawing the vector, you just draw a line from O to that point P, so that would be vector OP, drawn in 3 space. So you need to show those lines 1, 2, and 3 to show how you got to that point, because you can't just draw the point without those kind of bases, because just drawing a point on, trying to represent a 3-dimensional point on a piece of paper is next to impossible unless you show this kind of breakdown. Okay? All right. So these examples are very similar to the previous lesson. We are converting back and forth between the component form and the unit vector form. We're using the I hat, j hat, k hat. So here we're given 3 vectors in 3 position vectors in component form, and we want to rewrite them in using the position vectors, the unit vectors I hat, j hat, and k hat. So that's fairly easy to do. So remember, these numbers represent the scalar multiples of I hat, j hat, k hat, so we're just combining them together in one expression. So this would be 2I hat plus j hat plus 3k hat. So those numbers 2, 1, 3 come from the component form. And then OQ, I'm looking at negative 3I hat plus 1j, or just j hat, minus 5k hat. And then the last one, OR, this one you just have to be a little more careful. That would be 0 times I hat, so that's, you don't have to write that, plus 2j hat, so we do write that, plus 0k hat, so we don't have to write that, so we're just writing the non-zero component elements of that vector. Okay, now this part goes the other direction. We have these vectors in terms of unit vectors, I hat, j hat, k hat. We want to write them in component form, so this is just going the other direction. So OP, looking at the multipliers of I hat, j hat, k hat. So it'd be 1, negative 2, negative 1. Make sure you put them in square brackets because that identifies the vector instead of the point. Then we have OQ. So if I'm looking at it's OS. Sorry. OS is just 3K. So remember, K is the third component. So in terms of I and J, I have 0 of those, but I have 3 K hats. So write it like that. And then finally OM. I can see I've got scalar multiple for I hat is 2. I don't have a j hat component, so that would be a 0 there. And I have negative 6 k hat, so that goes in the third spot. Okay, so this is just an exercise moving back and forth between the two forms. Okay, now we're going to combine vectors in R3, and we've got the vectors currently written in the unit vector form using I hat, j hat, k hat combinations. So the vectors we're talking about are vector A, vector B, and vector C. And we want to do combinations of vector A, vector B, and C to come up with the result. So we're going to do this in 2 forms, but before I do that, I'm going to first of all write vector A, B, and C in component form, so I can reference this. So A would be negative 1, 2, 1. Vector B would be, so there's no I, so that's a 0, 0, 2, negative 3. And finally, vector C would be 1, negative 3, 2. Okay, so now I'm going to answer the question with two different processes. The first one, we're just going to use component form. And the second one, we'll use the standard unit vectors. Okay, so we want two things. We want 2a minus b minus c, so 2a minus b minus c. Okay, so basically I'm going to replace a, since I'm using component form, I'm going to replace a with the component form. So that would be 2 bracket negative 1, 2, 1 minus b, 0, 2, negative 3. Running out of room here. And then minus c, which would be 1. Let me just make a bit of room here. 1, negative 3, 2. Bump into the other space. And now we just, well, the first thing I would do was, if there's any multipliers in front, I would multiply them out, and including the negative sign, I'm going to treat that like a scalar multiple of negative 1. So if I multiply the first set of components by 2, I get negative 2, 4, 2. And then I'm going to multiply this by negative 1, and I'm going to change it to an add just to make it a little bit easier to deal with. So I'm basically flipping all the signs inside because I'm changing it to an add. And then same thing with the third. Flip the signs inside, changes it to an addition. So 1, 3, negative 2. And now when I add them all together, so I've got negative 2 plus 0 plus negative 1. Sorry, that should be a 1. C is a 1. Just make sure I did this right. 1, negative 3, 2. So that changes to negative 1, positive 3, negative 2. Okay. Okay, so if we add up the components here, we have negative 2 plus 0 plus negative 1, so that would be negative 3. For the y components, we got 4 minus 2 plus 3, so that would be 2 plus 3 is 5. And then for the z component, 2 plus 3 is 5, minus 2 is 3. So that's our component representation of 2a minus b minus c. Okay, if we do the second calculation, they want vector a plus b plus c. So this one should be a little bit easier because there's no multiplication or subtractions. So we just have vector a, negative 2, 1, 0, sorry, negative 2, 1, 1, negative 1, 2, 1, plus vector b, 0, 2, negative 3, plus vector c, 1, 3, sorry, negative 3, 2. And we can add these all at once. We get negative 1 plus 1 is 0. 2 plus 2 is 4, minus 3 is 1. 1 minus 3 is negative 2 plus 2 is 0. So there's the component representation of vector A plus vector B plus vector C. So let's try the same thing with using standard unit vectors. So probably going to need 2 lines for this now. 2a minus b minus c. is going to be, so this time we're just going to leave the representation that was given. So vector A, put it in brackets, negative I hat plus 2j hat plus k hat, and then minus vector B, which is 2j hat minus 3k hat, and then we'll add the last one on a new line. That would be minus c, minus vector c, so that's going to be in brackets I hat minus 3j hat plus 2k hat. Okay, so now we're going to just expand this. So I'm going to get negative 2i hat plus 4j hat plus 2k hat. So that's the first part. And then minus 2j hat plus 3k hat. And then minus I hat plus 3j hat minus 2k hat. And now we can combine, basically think of it as like terms. We have negative 2i hat, we don't have any I hats here, plus, minus 1 I hat. So that would be, so that's not a minus, that's a plus. So minus, hold on one sec. Yeah, so minus 2i hat minus 1i hat is minus 3i hat. And then we've got, for j hats, we got plus 4, plus 3, 7, plus 3, hold on, so plus 3. Okay, so for j hat, 4j hat minus 2j hat, so that'd be 2j hat plus 3j hat, that's a 5 plus 5j hat. And then finally k hat, 2 plus 3 minus 2, that would be plus 3 k hat. Okay, so that's our using standard unit vectors. You can see that these two forms are give you the same result. We've got a negative 3, positive 5, positive 3. So let's try the last part. So this is vector A plus vector B plus vector C. So that will be negative I hat plus 2j hat plus k hat. So that's your vector A. And then vector B is 2j hat minus 3k hat. And then vector C is positive plus vector plus I hat minus 3j hat plus 2k hat. Okay, now if we add these together, we're going to get, in terms of I hats, well, we only have one here and one here. So we have a minus 1 I hat plus 1 I hat. That cancels out. 0 I hats is 0. J hat, we have plus 2 minus 3. So that leaves 1 J hat. And then K hat, we've got 1 minus 3 is negative 2, plus 2 is 0. So we're left with just J hat as our answer. And you can see that these two answers match up. They're equivalent because I've just got the one coefficient of 1 for the y component. Okay, so you have to understand both methods, but I think most people, given the choice, would use the component form. Just less clutter with the I hat, J hat, K hat, but really working with the same numbers, just without the variables, if you want to call it that. I hat, J hat, K hat. Okay, so let's go on to the last example. This would be a more typical question you would get on a test. You're given 2 points in 3 space, A and B. You've got the X, Y, and Z coordinates, and we want to measure the magnitude of the position vector OA, the magnitude of position vector OB, the vector AB, the components of it, not the magnitude, and then the magnitude of vector AB. So before we do these calculations, and this is an absolute essential, we want to actually represent the position vectors OA and OB. The numbers will be the same as the points, but it's important that you represent this as a vector now. So position vector OA would have components 7, -11, 13, and position vector OB would have components 4, -7, 25. Because we're going to be working with these vectors when we do these calculations. So the first calculation we want is magnitude of vector OA. And once we know the components of the vector we're getting the magnitude of, it's just the sum of the squares of each component and then square rooted. So it's going to be 7 squared plus -11 squared plus 13 squared. If we square those and combine them, we get positive 339. Take the square root of that. Our approximate answer is 18.41. We don't know the units, but we leave it as a number or put units if we want. Just the word units. The second one is the magnitude of vector OB. So this is very similar to what we just did, except we're working with these components. So the magnitude would be 4 squared plus -7 squared plus 25 squared. Add those together, take the square root. That would be the square root of 690, which is approximately 26.27. Okay, and then the third one, this is different. We actually want the vector components of AB. So remember, the all-important formula is vector AB is vector OB minus vector OA. So this is where we do our vector math. So vector OB, we have the components there. Let's write them out. 4, -7, 25. And we subtract the components of vector OA. 7, -11, 13. And now we just do the math, the subtraction of each component. So 4 minus 7, -3. -7 plus 11, 4. And 25 minus 13 is 12. So that would be the component representation of vector AB. And finally, we want the magnitude of vector AB. So we just created the components, which you'd have to do first anyways. So that magnitude will be the square root of the components of vector AB. Of the components, sum of the components squared. So -3 squared plus 4 squared plus 12 squared. That works out to 169, which is a perfect square. So that's exactly equal to 13. Okay, so that's a pretty typical question from this part of the unit. So we've got some practice questions for you to work on. Practice these skills, and that's it for today. Hope that made sense, and we'll see you on the next lesson on vectors. Take care.